As you know, today Dr. Massimo will present, and he's the managing CEO and managing partner at ASDEA Software, and they do come up with a lot of OpenSees related tools and stuff. So, and today he'll be talking about the tips and techniques for all of us to model RC frames. So, Massimo, it's all yours now. Thank you for presenting.
Okay, thank you, Pavan. Let me share my screen.
Can you
allow me? Yeah, can you allow me share my screen, please?
Can you share now?
Okay, yes, I can. Thank you.
Oh, awesome.
Here I am. Here we go. So today's presentation, I'm going to talk about frame modeling in OpenSees. I will not talk about some specific practical example. Rather, I will talk about some of the theoretical and implementational aspects of what are the most widely used elements in OpenSees, probably the displacement-based and force-based elements. That's why I call this, I give it a title like tips and tricks. So these are the contents. A brief introduction about the displacement versus the force-based beam element, and some of the problems that you may have. Some of them are related to the theoretic background of this formulation. Some of them instead are related to the implementation that you have in OpenSees. In any case, I would like to give some tips on how to use them, because there are some cases in which you can do some strange mistakes. So I would like people to avoid it. So the first point would be about softening and mesh objectivity, because basically we mainly model reinforced concrete structures, so we have to deal with softening, and this is a huge problem. Then how you can include shear response in beam elements in OpenSees, and once again also here you will find differences in displacement versus force-based formulations. Same thing for torsional response. Probably torsional response is the least important for the majority of the people, but also in this case there are some differences, and also some differences are encountered in the use of the element distributed loads. So after I give this brief introduction with all the examples, I will move to some more practical examples about a structure. So first I will explain very briefly the main three approaches that you can use with OpenSees. I'm pretty sure most of the users of OpenSees are already aware of them. So I will just show how to do them right quickly. And then I will try to include also beam column joints using the scissor-model. And here I will show you how a pre and post processor such as STKO can actually help you in speed up the creation of the model. Because when you want to include, for example, beam column joints, your model becomes more complicated. And so writing the TCL file manually can take time. And then the last few minutes, I will talk just a little bit about STKO, mainly about the motivation that we had, the reasons why we decided to create this tool. I will not spend so much time about speed up creation of the model or in-depth interpretation of the results, because when I will talk about all the previous topics here, I will use STKO to show the results, so you can already understand how helpful it can be to visualize the results. So let's move into the first topic, displacement versus force beam elements. Now, basically, everyone knows the main difference. The displacement-based follows the standard finite element formulation, where the displacement is the unknown, and the element computes the strain from the displacement, and then these strains are sent to the section. The section gives us the stresses. While the force-based is kind of different, because the force-based assumes the distribution of stresses along the element and then computes the strains with an iterative process. Now this kind of theoretical background and implementation leads to many different aspects with respect to the displacement base. So the first one that everyone should take care of is the softening regime and what is called mesh objectivity. Basically, the problem is that whenever you have strain softening in constitutive models, the presence of strain softening leads to the non-uniqueness of the solution. This happens because the displacement field becomes discontinuous in the sense that you have displacement jump. And this is not particularly good for standard finite element method, because when we use the finite element method, at least the standard finite element method, we assume that our solution is sufficiently smooth and can be derivable. But of course, when you have displacement jump, this is not possible anymore. However, we still want to use stress strain models because this is what we have, and we have to deal with strain softening structures, for example, reinforced concrete structures. So what happens when you use softening models using a stress-strain relationship with discontinuous displacement is that you have a strain localization. The problem is that all the deformation localizes into a narrow band of elements if you're using continuum elements, or inside one element if you're using beam elements. And the problem is that the energy dissipation now depends strictly on the element characteristic length. And as we will see, it is not necessarily the size of the element, it can be the size of the integration point, but what is important is that the solution depends on the mesh, and this is something that should never happen. And so with respect to the strain softening response, displacement-based and force-based element behave differently, so you have to take care about it. So I will show a simple example about a simple column, okay? So first we will load it in the vertical direction, and then we will push it in the horizontal direction. And we will see what happens if you model it with one force-based element with 5 integration points, one force-based element with 10 integration points, one displacement-based with 5 integration points and 10 integration points, or with 5 displacement-based elements with 5 integration points, okay? So before I go ahead, I would like to show you the structure of the files that I will send you. So you will have the PowerPoint of the presentation, an Excel support file that we use for calculation during these examples. Then all the topics about displacement versus force-based element are in the folder beam element, and you will see all of them here. And finally, we have a folder called 3D structure with the final examples. Okay, so now we open up the first file. Okay, here. Beam element. Softening and mesh objectivity. I will first open the first one where you don't take care about regularizing the response. So you will see that using the same material model with all those different elements, you will obtain completely different results. And then I will show you how to regularize them. So this is the first one. I'm not going to tell you about how to model this in STKO. Okay. When I will share these files, I will share both. Let me show you. Both the STKO file, the STKO output, but also all the TCOL file generated by STKO. So if you don't want to use STKO, you can simply use the TCOL file that are already generated, okay? So you're not bound to use STKO by any means. Okay, so here in this file, we have 5 columns. The first one is a force-based element with 5 integration points. The second one is the same force-based elements. And here we have the finite element assigned here. I click on select. The first 2 are force-based. All the other 3 are displacement-based column elements. Now the first one has only 5 integration points. Okay, so Lobato-Gauss integration with 5 integration points. The other one has 10 integration points. Then we have displacement-based, one element with 5 integration points, one element with 10, and here we have another column discretized in 5 parts, okay? So 5 elements with 5 integration points. Now, all of them will use the same concrete model, okay? A simple concrete 01. Let me show you material parameters for this. Okay. Okay, simple model here. In this model, you cannot specify the fracture energy, but you can specify the ultimate strain. So in some way, you can adjust the fracture energy here. Then a simple model for the steel. I'm going to go to Pinto model. That's fine. This is pretty well known. And then we have a fiber cross section. Okay, so in this first example, we will only take care about PMM interaction. Okay. So when we do this analysis, you can simply run it, and then when you have the results, if you want to do it with STKO, you already have the output file. Otherwise, you can simply take, let me show you. You can simply take the STKO files, because STKO generates STKO files with a main TKO that sources all the others. And they are a pretty simple structure. So you have nodes, elements, materials, and then finally the analysis steps. Here you have a recorder made for STKO, because basically we introduced in OpenSees the MPCO recorder that records everything or everything the user wants into an HDF5 based database. So if you don't want to use STKO as a post-processor, you can simply replace these lines with the recorder that you want, okay? And you can use all the other. You can find some strange things here in the analysis, because we don't use the typical analyze command in OpenSees, or actually we don't use analyze, for example, 100 steps. We have an adaptive time step here. So we analyze one step at a time, then we check the convergence, number of iterations. If necessary, we adapt the time step. But except these small differences, everything should be pretty clear if you know already OpenSees. Okay, so when you run the analysis and you obtain the results, now I'm going to load it back in STKO, softening and mesh objectivity. Okay, so we have these 5 columns, and here I want to visualize beam diagrams so that we can see what's going on. Okay, so first of all, let me go with beam diagrams in STKO. You can visualize both local forces, which are forces at the element end nodes, or values at the Gauss points, so section deformation or section forces. Okay, and in this case, let me show you the section deformation. Let me switch off the grid, we don't need it. And let me go in the front view. And then I want to visualize the curvature in about the y-axis. Okay, so first of all, they are loaded at in the same way. So one thinks that the behavior will be the same. Now let's see what are the results extracted in all the top nodes. Okay, so all the top nodes are basically they have an imposed displacement applied in the x direction. So we can read both the displacement and the reaction here. Okay, so I'm going to extract the result on nodes, and from the second time step, because the second time step is the one where we push the structure. And then I want to plot displacement versus reaction force along the x direction. 5 nodes. Okay, so the first one, node number 2, is the force-based element. Okay, first of all, you see that there are huge differences between one another. So the first one is the force-based element with 5 integration points. Then you have the second one, and you can see already that there is a major strain localization here, which is always one element, 10 integration points. The response is the same up to the peak here, but then when the strain softening appears, this one dissipates much less energy. Okay, so the post peak is not the same. The response is not the same. Same thing happened for displacement-based elements. Of course, there is a difference now. These two displacement-based elements, they have different number of integration points, but they are just one element, and they have the same response. So you can see node 4, it is node 6 and node 8. You can see that, as you can see, the overlap. So changing the number of integration point in the displacement-based does not change anything. Okay, but of course, if you discretize the element, then there is a difference between this one and the red line. Okay, so the red line once again dissipates less than the others. So now what we are going to, what is this first difference? As I told you here, strain localizes inside what is the characteristic length of the element. Now the characteristic length is typically related to the size of the finite element when the displacements are linear, when you have low order integration schemes. But when you have higher order integration schemes, or you are using mixed finite elements such as the force-based, the characteristic length is not the element length, but it's actually related to the integration scheme. So for example, here in the displacement-based, as you can see, the entire element localizes, the curvature is linear, here is continuous. While in the force-based elements, the curvature is not continuous because of course the element assumes a continuous moment, not the curvature. And then you have a strain localization just in the integration point. So changing the integration point in the force-based, change the response. While for the displacement-based, if you increase the number of elements, the localization happens only in one element. So the element is smaller, the less energy is dissipated. So now what happens is that whenever you have to include strain softening, you need to regularize the response. And then, of course, there are other elements, for example, the one introduced by Professor Scott, we will talk about it later, that will remove this kind of problem. Okay? But if you use standard displacement-based or force-based with standard integration rule, you have to take care about strain regularization, fracture energy regularization, sorry. So basically here I had another file. Let me open it, which is the strain softening and mesh objectivity regularized, which is basically the same as before, okay? But instead of using the same concrete for all the elements, I created other concretes. Now we'll explain you why. So first of all, we started with the first one that had 5 integration point, Lobato. Okay, now as we can see, just one integration point localizes. Now in the Lobato integration scheme, the bottom integration points here, the top and bottom integration points, they have a weight which is the 5% of the entire length. So if you want to see them, you can go in the source code, you can open the Lobato beam integration, and for 5 integration points, you can see here you have 0.1 and 0.1, but all of them sum to 2, so you have to divide it by 0.5. So here you have 0.05, 5% of the length of the element, okay? While the entire, well here, for example, we used 10 integration points, okay? And if you go back here, you see the 10 integration point Lobato scheme here. You can see that it is 0.0111 once you divide it by 2, okay? So basically what we have to do is to, this one will dissipate less because the weight, the size of the integration point is less by a factor of 4.5. So what you have to do is to change the concrete response, increasing the fracture energy by 4.5. Okay, no, so the fracture energy regularization, you have some reference here. Of course, it depends on the kind of, in this case, concrete curve that you use. What you have to make sure is that the area under the softening regime, the bounded area under the softening regime, should be scaled by a factor which is the reference length divided by the characteristic length of the element. Now, in this case, the reference length, let's say, is the one of our first column. Assume that this is the right solution. This one gives us a scale factor of 4.5 here. Okay, so if you develop this equation, you end up that you can calculate the ultimate strain for a regularized response. Okay, now in this case, it is almost, this one is almost 4.5 times the last one. Okay, the previous one. So here we have the first concrete that we used before. Okay, so this one was 0.03. And here you have an Excel file that you can use for this, and I did the computation already. And you can use this one for doing the strain regularization of this kind of concrete models, okay? So you put your input files here, your input data, you put the scale factor, now in this case it was 4.5, and it gives you the ultimate strain for the regularized compressive response. If you use concrete 02, you also have to regularize the tensile response, but it is not this example. Okay, so here we only need to regularize the compressive response. Okay, so basically you go back here, you create a copy of the material, and you change the ultimate strain in such a way that the compressive fracture energy is regularized. Okay, so in this way, I do the same. Then of course I have to create another fiber section that points to that material. And I can assign it to this one, okay? Now, given this difference, these two models will behave the same. Okay. Now we have to do some other changes to the others. So this one is a displacement based with 5 integration points. So this one actually needs an integration rule that is scaled with another factor. You will see them. It should be this one. Let me see. No, this one is the last one. Or is this one? Yes. From the previous response, you could see that in this case, for the force-based with 10 integration point, we need to increase the fracture energy. Okay. For the displacement-based, actually, we need to decrease it. In fact, the displacement-based localizes in the entire element. So the entire element is actually 20 times larger than the integration point here. So that's why we have a beam integration rule with a 0.05% scale. Okay, so I took basically this concrete model, I did the same, but instead of increasing the fracture energy, I decreased it. Okay, so you go here, you put your scale factor, in this case it was 0.05, and you obtain the new fracture energy. Okay, and then I did the same for the displacement based here, which is divided in 5 pieces. Okay, which is basically the previous one, so regularized by 0.05 times 5 times. Okay, so once you do all these tricks and you put them together, they should give you the same response. It's not going to be exactly the same, and I will show you, but they will be much closer than this one. Okay, so once you run the other analysis, you can load the output, which is this one. Once again, let me go to the beam diagram. Let me move to section deformation. Then I select all the nodes here. So force-based with more integration point, displacement-based, and displacement-based discretized. Then I extract the chart data here. Once again, stage number 2, displacement versus reaction force in X. Okay, so now the responses are much closer in the sense that you have the black one and the green one that are the two force-based. As you can see now, they are much closer here. Of course, this kind of procedure is not perfect because it assumes a constant state of deformation, but in this case you have banding, so it is not exactly a constant state of deformation, but the responses are much closer. So the black one is the force-based with 5 integration point. Then you have the green one, which now is not down here, but it's closer to the black one. Then you have these other two displacement-based, so only one element with 5 or 10 integration points. And now they are still regularized, but they are not so close. They are better because now they localize, but they are not so close to the exact solution as the others. Okay. But if instead for the displacement base you discretize them, okay, and you apply a proper regularization, which is the red one, also this one can match the response of the force base. Okay, so basically here what happens is that let's examine what is the difference for the force base, for example. Now, even if you regularize the response using the fractional energy regularization, the global response will be the same, but locally you will always see a difference. Okay, so if you have only one integration point, and if we run an animation, probably it's easier to understand. Okay, let's go back to the beginning. Okay, when you start here, the curvatures are pretty much linear. Okay, then you start having some sort of, but also here, when you have the first cracking, you can already see that the two force-based are the same. They behave the same because the response is still stable. When you look at the displacement-based, you can see that there is something strange because here you can see a negative curvature where it should be 0. But then as soon as you discretize the displacement-based, you don't have a continuous solution for the strain, but it is much better. Okay. But when you go here and they start localizing, Here for the force-based, you can see a localization, okay? So the moment is assumed linear, but the curvature is not linear anymore. That's why a single force-based element can represent better the nonlinear response. Okay, you can see localization here. The displacement-based, they're still linear, okay? But if you discretize them, you can start seeing some sort of regularization, some sort of localization, okay? But the amount of strain that you see will never be regularized. So actually what you regularize is the amount of dissipated energy. You will always see a difference in the amount of strain, because remember that this is not a real strain, because as I said, you should have a displacement jump, but you don't have it, okay? That's why you compute this kind of strain strength. But the most important thing is that at least the response is regularized, okay? So going back to the presentation, well, I will give some summary later on. So basically, these are the first problems, the major problem that you have with when using strain softening. Okay, so pay attention to what kind of finite element formulation that you use, either displacement based or force based. Okay, and be prepared to do this kind of regularization. Otherwise, there will be the beam with ingest element that will solve this problem in a much nice fashion. Okay, so let's move to the next step. The next one will be the shear response. Now, probably not everyone has included shear response while they have been using the beam elements in OpenSees, but if you want to do it, you have to take care, because there is a difference between the displacement based and the force based. And here I wrote bug. I'm not sure if it is a bug or if it is meant to be like that, but fortunately we have Professor Scott, so we can ask him what they think about it. I will first explain what I found, and then let's see if it is something that can be solved or not. So first of all, how can we include the shear response in OpenSees? So when we start with fiber section, you know very well that we can handle only PMM interaction. You don't have any shear deformability, so basically we have an Euler-Bernoulli beam. If we want, we can include shear deformability to obtain a Timoshenko-like response, but we need to use the section aggregator. Okay, so we can aggregate the shear response and eventually the torsional response to the PMM response. Okay. So other few points that you have to keep in mind: shear forces at the element level are always present because of equilibrium, of course. But if you want to look at the shear forces at the section level, you can only see them if they are included with the section aggregator. Another point that you have to keep in mind is that the shear stress strain law should always be regularized as usual, okay, depending on if you're using a displacement based or a force based. And as I said, you will see that displacement based elements and force based elements behave differently. So always take care when including shear deformability. Okay, so you can find the files for this example here. So let me open up the example for the shear response. Here I give a first example, shear without shear. Okay, so this is the first example before. So here I have one force-based element here, and the other one is a displacement-based element. Now, keeping in mind the problem of strain regularization, here I use the same concrete element. Okay, so instead of changing the amount of fracture energy, I discretize this element here in 20 parts in such a way that the element length here, down here, is the same as the integration point at the bottom of the force base. So they will give the same response, okay? Now, if you run this analysis just with a fiber section directly sent to the material model, so without any section aggregator, the output will be this one. So you go in beam elements, you go in shear without shear. Okay, let me close the surface map. And once again, I want to show you the beam diagram here. Okay, section deformation. As usual, we have the key curvature in Y. Okay, so now the response will be the same. Let me just extract the displacement versus reaction curve, so that then we can compare it with the one with shear included. Okay, so when I extract this one, I go in stage 2 as I did before. Okay, so this is the response for the force-based and displacement-based, properly regularized, okay, without any shear deformability. Now, so this one is fine. Then you can open up the other file, which is shear with shear. Okay, this one. Where basically, instead of using the fiber cross-section directly in the beam property, I created a shear law. Now you can use whatever uniaxial law you want. Here we were using a modified Ibarra-Medina-Kravinkler. Here you can see some of the parameters. And this is the response that we want in shear. Okay, and then once you have this shear response, just a second, I have this one. Okay. When you have the uniaxial response in one direction and eventually also in the other, if you're interested, you can create a section aggregator. Okay. And with section aggregator, you can use the cross-section for the PMM interaction. And then you can say, okay, I also want to include shear deformability using the shear law that I previously defined, okay? And assign this one to both the force-based and displacement-based. So actually what I expect, and actually here I gave a shear response in such a way that it should reach a shear failure before the bending failure, about that 60 kilonewton here. Okay, so let's see what happened. And if you run this model and you open, let me close this one. First of all, I want to keep this curve for making a comparison. Okay, but it's not necessary actually, because you will discover why. I open the shear with shear now. Okay, this is one. I do the same as I did before. So beam diagram, and I'm going to extract the displacement versus reaction curve at the 2 points here. And we expect that they should behave the same. So they should fail before the bending failure. But unfortunately, what happens is that the shear response is visible only in the force-based element, while the displacement-based behaves the same as it was before. Now, I wasn't expecting this. That's why I reported this here. So I asked, why is the finite element, why is this displacement-based not representing the shear failure? But actually, it is not related to the finite element formulation in this case. It's actually an implementation detail, because if I go on this section deformation, okay, and I go to the curvature, okay, here I can still see that the displacement-based element localizes in curvature, okay, so it is conformant with what we see here in the global response. And so I say, okay, let me see what is the shear deformation, okay, in Z. I only have shear deformation for the force-based. I don't have any shear deformation for the displacement-based. So actually what happens is that if you go in the source code and you compare the force-based and the displacement-based, yeah, for some reason I cannot click on it.
I have no idea. Hello? Oh, it's not us.
I think it was Massimo's
Yeah.
connection. Right? Just give it a couple minutes.
Yeah.
Sorry, hi everyone. Sorry, we had a problem with the connection here.
Oh, that's fine. Cool.
Okay. Let me connect back to my computer.
Yeah.
We had some problems with the internet connection these days.
Okay.
Still connecting with my computer. Just a second. Okay, here we are. Okay, so I said, I think we have seen that. I don't remember actually when I got offline. Okay, so looking at the results, we have seen that the force-based, the displacement-based does not take into account the shear deformation. So I went into the source code, and if you look at the force-based and then at the displacement-based, and you go in the update method, which is the method that the element uses to do the state determination of the cross-section, you can see that the force-based correctly takes care of all the responses, although it does it in a different way with respect to the displacement-based. But then if you go in the displacement-based in the update method, they simply do not take care about the shear response. Okay, so that's why you always see 0. So basically, taking this into account, you have to understand that if you want to include shear deformation, at least now, you should use the force-based. Now, actually, I don't know the reason for this, but fortunately, we have Professor Scott, so I would like to ask if it is probably I missed something, and the displacement-based is supposed to not to support shear, or probably it is kind of a bug or something that is missing. Do you have any clue, Professor?
I think that was by design for the displacement beam column to just be a Bernoulli type formulation. So there's no shape functions for the shear. But there's some other like Timoshenko beam columns in there that take into account the shear. But it's, I guess the point, it was intentionally left out just to keep it as a simple, Bernoulli formulation, nothing more, nothing less. So
okay, perfect. So actually,
it's not a bug; it's a feature, right, or an implementation decision. Yeah.
Perfect. So I was not sure about this. That's why, fortunately, you were here, so I could ask you. Because actually, I was supposing that also the displacement base was using it. Then I discovered it a few days ago. So basically, if you want to use shear deformation, so you should use the force-based element, or there are some other Timoshenko elements, as the professor said.
I don't think that the Timoshenko beam columns really been tested that much. So I would.
Yeah,
I wouldn't trust it at this point, but
yeah, I've also seen new mixed beam elements. I don't know how they work, but probably they would work.
Yeah, they're a lot like force-based.
Okay.
So yeah.
Okay, so thank you, Professor. Yeah, so basically, if you want to include shear deformation, for the moment, at least use the force-based element. Then another difference that I've seen that probably is not so important, but because I imagine that not so many people want to use torsion, they're not, I mean, they don't care about torsional response. Also in the torsional response, there is a difference, and now this depends actually on the, in part depends on the finite element formulation, so the difference between, the theoretical difference between displacement-based and force-based, but in part it depends also on the implementation. So torsional response. Let's go back here. Here you will see here torsional response. Once again, you can include torsional deformability with the section aggregator, and also here displacement base and force base behave differently, partly due to the theoretical background of the force based and the displacement based, and partly is due to the implementation. Okay, so let's go back to the torsion example. So new, and also here, let me open up the torsion example. So you go in beam elements and you have torsion. Okay, so now they are force-based and displacement-based, Same discretization, same number of integration points, because now actually in this kind of example, torsion will be constant. So there is no problem of strain regularization in this case. So the two columns are the same as before. They're simply fixed at the bottom, and then you have an end torque here. So same fiber section, even if in this case you don't need a fiber section actually. And then you have a torsion law. I basically have chosen the same as the shear that I used before, okay, but with different parameters, of course. Okay, so this stiffness here is about the J of my cross section times the G. Okay, and the shear response now it has the same shape I use for shear, but I want to focus only on the initial part because it's here that we can see some differences. Okay, so you go in the beam section aggregator, you can do the same as you did before, but instead of including the two transverse shear, you include the torsion. Okay, so actually the model is quite simple. You have a fix at the base, all the 6 degrees of freedom, and you have a prescribed torque at the top. Okay, in such a way that I go just a little bit after the first degradation of my torsion diagram. Okay, so now how do you include this one? As I said, if you want to include a nonlinear torsion, you have to do it through the section aggregator, because otherwise you can include some kind of torsion with the fiber, but only only for an elastic response. Now, in previous versions of OpenSees, you were not forced in using the GJ parameter. Okay, it was optional. But now in the new version, it is mandatory. So you always have to use a GJ parameter. Okay, so now I was wondering what happens if I change this value, but I also include a torsion in the section aggregator. Okay, now if I use 0, you will see that they behave the same. Okay, and if you run this analysis, basically you have this output. And then you will see what happens if I slightly change those values. So you go in torsion, shear with shear, sorry. Well, I called it shear with shear, but I have to change the name, of course. And let me go to the beam diagram plot. And I want to see the section deformation for theta. Oh, first of all, when you have the torsion included in the fiber cross section, you only have one degree of freedom here for the torsion. But when you include it also in the aggregator, you have 2 of them. This is an implementation choice. Probably before it didn't happen, because if one wanted to use a nonlinear torsion, he used to include it in the section aggregator, but didn't use the GJ parameter in the cross section. But in the current version of OpenSees, it is mandatory. So if you want to include a nonlinear section, you end up having 2 components in your sections of torsion. One is the elastic response given by the fiber section, and the other is the nonlinear response explicitly given in the section aggregator. Okay, so I was wondering what happens if I include both of them. Now, if I put 0, imagine that the only one that plays is the second one, and in fact it's like that. Okay, so it is perfectly fine. There is no difference between the displacement-based and the force-based. Okay, so if I try to extract a graph here, extract chart data on nodes, and I want to see, this is only one stage, there are no 2 stages. Okay, so rotation on top, rotation about the z-axis versus the reaction moment about the z-axis. Okay, they should give me the same response, and they're perfectly the same. Okay, so pretty much exactly as I stopped in the material test here, and they give me exactly the same value that I was expecting. Actually, here I was expecting something different. I was expecting the displacement-based element to give me this correct response, but I was expecting the force-based element to give me 0. Sorry. I still have unstable internet connection. I apologize.
No, that's fine. Lockdown.
Okay, so while this one tries to connect, I keep on saying, so it was expected the displacement base gives the same torsional deformation to the cross section, to the fiber cross section, to the section aggregator. So I expect the result in terms of torsional forces to be summed. So zero coming from the fiber cross section plus the real response given by the section aggregator. But then for the force-based, the way it is implemented, I was expecting that responses were connected in series. Okay, so the softest one wins. That's why I was expecting zero. But actually, this doesn't happen if you apply an exactly zero value in GJ. Okay, so now let's see what happens instead if I apply a very small value in GJ. So I go to the fiber, because I've seen in many old OpenSees code, people used to use a very small value just not to have a singular response, but they didn't care about the real GJ value. So if I put some value like 1 to the minus 10, just to put a number, I obtain what I was expecting. So I run the analysis, back to the post-processor, reload it. Okay, now I see a very small deformation here. I don't know why we're having this kind of, yeah. Okay, here we are. So if I look at the response now, the displacement base is still correct, while the force based is almost zero, because now it is actually how it should behave. So the force based not compute a unique strain for all the components of the cross section. It just imposes the same stress. So if one of them has a smaller value in stiffness, it will win. Okay, so like if they were connected in series. So for a force based, you should use the same stiffness in the GJ and in the section aggregator. But if you do that, the displacement based, they will be connected in parallel, so it will be much stiffer. So for example, if I go here, I go to the fiber section and I put the same value, like it was 3, or actually a higher value, just to make it stiffer than the, it was 14, 13, then I give 1 order of magnitude more. And then I run this analysis. Now the force based will give me the exact result. Okay, which is here. It goes in plastic regime here at a value of 60,000, which is here, while the displacement base behaves almost elastically. So the main difference is once again depending in part on the finite-length formulation. So the displacement base gives the same deformation to both the torsion components, while the force-based put them in series. Okay. So once again, what is the solution? Fortunately, I've seen that if you put 0, exactly 0, in the fiber section, you obtain the exact solution. So basically here, if you want to use a nonlinear fiber, a nonlinear property in the section aggregator, pay attention to use exactly 0 here, because it works for both the displacement-based and force-based. If you use a small value, the force base will not work. Okay. If you use the same or a larger value, the displacement base will not work. Okay. So this one is fine. And then the last point that I had about the beam elements was about the element distributed loads. This is actually pretty straightforward, but probably not everyone is aware of this. So Another difference due to the now to the implementation of the displacement-based versus the force-based is how the element loads triggers nonlinear effects inside the elements. So nonlinear effects given only by the element loads are possible only with the force-based element. Now, actually, this is quite simple to visualize if you go and open the last example, the beam element, which is element loads here. Okay, there are two simple beams. They are fixed in both the degree of freedom. Only the x degree of freedom is free. So you have a roller here. And then the only load that you have is an element distributed load along the local z direction, which is along this direction here. Okay, on condition, both of the parts are fixed, and then you have distributed load. I use only one element in the mesh. Okay, so I should have no rotation, no displacement, only some actual displacement if my cross section is nonlinear here. Okay, and in fact, I'm using the same fiber section as before. Now, if you run this analysis, let me create a new file for the post processor. And you go with element loads. Okay, so just one element. You will see, first of all, that there is a difference in the displacement magnitude, while you should expect that none of them displace, but only the force-based displace and displace in the z direction. Okay, because actually, as we expected, the distributed load is triggering nonlinearity inside the beam. And when you have reinforced concrete, of course, you have a shift of the neutral axis, and so you have an actual displacement. Okay. But the same thing does not happen in the displacement base. In fact, if we go and look at the beam diagram, okay, if I look at the beam diagram and I look at the local forces, I can see pretty much the same response in the bending moments. Okay, now they are constant because they should be negative, positive, negative, but since we have only two values, I do a linear interpolation between them. Okay. But if I try to visualize them using the section forces, so one response for every Gauss point, I can see that the force-based has actually section forces, while the displacement-based has no section forces. Okay, this of course is due to the implementation and the theory about the force-based and displacement-based, because of course here all the degrees of freedom are fixed, so there is no deformation computed from the displacement. And so the forces are only added like in a post-processing, okay? So are only added to the element for computing the element and node forces, but these forces are not passed somehow to the cross sections. The force base instead does compute the section strains iteratively, okay? So during each iteration, it applies the section forces, and so every section is aware of the amount of force that is there. Okay, so basically this other difference, once again, also in this case, we use the force-based element if you are not sure. Of course, everything gets better if you discretize as usual. Okay, so once again, if I try to increase the number of elements, you will see that the response pretty much will match. So reload this one. Okay, so once again, here I try to visualize now the section local forces, and I can visualize the bending moments about the y direction. Now you can see they are actually equal at the element level. You can see some differences, some small differences at the section level, because here they're perfect, but here there are some small changes. This is normal because you're using a displacement based. Okay, so you have jumps between one element and the other, but the more you discretize it, the more the responses get closer. Okay, so this one is the last example about the differences between displacement and force-based elements. Okay, so here I have a small recap about some rules that we have to keep in mind when we choose what element to use. So the first one, which is very well known for everyone. So if you use a displacement base, you need a fine mesh, okay, for nonlinear problems. One element is enough instead of force-based. Then the other problem is to take into account is the regularization of fracture energy if you're trying to analyze concrete structures. So displacement-based, the characteristic length is equal to the element. In the force-based, the characteristic length is equal to the Gauss point. Okay. Then you have the shear. Shear can be included in section aggregator, but only for the force-based, so not for the displacement-based. So displacement-based can only be Euler-Bernoulli. This one can also be a Timoshenko beam. Torsion is the same. Torsion has a difference, but if you include it in the section aggregator, set Gj equal to 0. For the displacement-based, this is mandatory. For the force-based, you can either put 0 or a larger value, because then since they are connected in series, the one in the aggregator will win, okay? But fortunately, since you can put an exact 0, will do the job, that's fine, so use 0. And finally, do not expect the element law to give you a nonlinear response with only one element in displacement-based, okay? While they do it for force-based. Okay, so this is pretty much about the comparison between displacement-based and force-based elements. Now we'll show you some examples about structure. I will first show you a small file that you can use to study how to implement distributed lump plasticity with finite length, which probably is the best element that you can use, which is the one by Professor Scott, where basically you can specify the size of the plastic hinge. So basically, if you don't want to deal with the problem of strain regularization, go with this one. So the old beam with the hinges that now actually is a force-based with a particular integration rule. Otherwise, if you prefer, you can use lump plasticity. Now I prepared a small file for this. I will not spend too much time because I think I'm running out of time. But I will show you how this file is structured, so you people can try to do your exercises with this one. Okay, so let me open a new post-processor file, and for the preprocessor, I go open, you go here, 3D structure, modeling approaches, and here you have 3 columns, okay? So the first one is the standard distributed plasticity. So in this case, for the first one, I was using same fiber cross-section for everyone. The first one has the same fiber cross-section in all 5 integration points of the Lobato integration rule. Okay, so the same one as we were using before. Then, as I said, there is this other alternative that for people that are not used to strain regularization, I recommend this one, of course, which is the beam with hinges. Or actually, that was the old command, beam with hinges, but now it can be accessed also with a standard force-based element, but using a different integration scheme. So here, instead of standard, you can choose hinge integration scheme, hinge Radau, or there are many others. You can refer to the paper of Professor Scott for this, which is a nice explanation about all of them. I use hinge Radau because I think it was the default in the beam with hinges command, in the old beam with hinges command. And you can specify the section at the 2 endpoints, the plastic hinge length, so you don't have to worry about the strain regularization, and a section tag for the inner part that can be either a non-linear or a linear one. Okay. Now in this case we used a linear one, but of course when you use an elastic element in the middle, both here and with the 0 length with the 0 length lump plasticity, you have to take into account that you should somehow reduce the 2 bending stiffnesses. Okay, so what we put here in STTO is actually a scale factor for the second moment of area of the 2 cross sections. Okay, so in this case, based on the bending on the axial load that I have in this example, I picked up a 35%, but actually this is dependent on the amount of vertical load that you expect. And so I call this one lump plasticity with finite length, because actually is something in between distributed plasticity and lump plasticity. Because actually the plasticity is confined in two specific parts, okay, so the two end Gauss points, but it is not a zero length, so it can still be a stress-strain relationship, okay. And finally, you have the well-known lamp plasticity. In lamp plasticity, of course, you should use zero-length elements. In the zero-length elements, you can only choose uniaxial model. Now, in this case, we have chosen a moment rotation spring with a modified Ibarra-Medina-Krawinkler. Also here, you can access, let me close this one, and I will show you the other Excel file that you may have here in 3D structure. Modeling approaches, and then you have support here. Basically here you can just drag and drop the moment curvature response that you obtain in your cross section. You input the plastic hinge length and you convert the values into the values needed by the modified Ibarra-Medina-Krawinkler, okay? And so you can basically put them here and run the analysis once again. So this one is pretty simple. I'm not going to talk about it. So this one will be a single element. This one, once again, is a single force-based element, but with a different integration scheme. Here, instead, the user can draw just one element, but then STKO will take care of duplicating the nodes, placing the Waldorfs here. Okay, so if you want to know how this model is generated, you can just, as usual, go to here, and you can go into elements, and you will see that you have one force base with Lobato, one force base with the Inchradau, and then for the compound element with the plastic hinges at the end, you have one elastic beam column in the middle, and then you have two zero-length elements, okay, with the proper material models. Okay, if you run this one, and then you can look at the results. It is here, 3D structure, modeling approaches. You can see the results for all of them. And then if I'm going to extract the displacement reaction forces at these two nodes and top one here, because here you have two nodes, okay, because of course there is a zero length in between. So you can pick up the end node, and once again you can extract the data, reaction forces. Okay, so all of them will match. So you can use this file to understand how to set up this kind of model so that they give you the same response. Okay, so how to scale the stiffness of the elastic element in the middle, and how to set up the equivalent uniaxial law for the lamp plasticity. That's fine. Okay, so as a last example, if I have a couple of minutes more, I'm not going to explain it to you exactly how it works, but I need it as an introduction to explain you the motivation why we decided to create a pre and post processor such as STKO. Now, pretty much you can see how it can be helpful in the post processing of the data, because you can actually understand what's going on even inside the Gauss points here. Okay, so you can look at the results in terms of beam diagrams as I've done before. Okay, so also this one will give you some kind of information about what's going on inside the finite element. Okay, but you can also look at Gauss point plot. For example, you can actually look at what's going on inside the Gauss points. Okay, if you want to go into deeper detail, you can watch what's going on inside the fiber cross sections. Okay, so in fiber cross section, you have some settings here. I'm not going to talk about this too much, but I can switch off, for example, the steel, and you can look at the stresses inside inside your fiber cross section. So you can actually understand that quite well what's going on in detail in your structure. So post-processing is quite clear. For pre-processing, now in this case, I've been doing very simple models. So doing them with a GUI or doing them by hand is not so complicated. But now imagine that you want to do something different. For example, I want to do an entire building, and where I want to use either distributed or lamp plasticity. I want to include shear, even torsion, but then I want to use beam column joints everywhere in my model. Imagine I have a lot of joints. For example, if I want to use the scissor-model like this one, every corner node here cannot be just one node and then beam and columns connect to it. Actually, I need to duplicate this corner node. Then I need to duplicate the end nodes of beam and columns. I have to create rigid offsets. I have to create kinematic constraints between them. And I have to create a zero-length element that connects these two nodes. And to this zero-length element, I have to give a proper, actually, moment rotation response that simulates somehow the shear deformation of the joint panel here. You can imagine that if you have a very complex structure, doing this for every joint can take a lot of time. Now, the nice thing about STKO is that you can actually, well, first of all, we made it to be exactly like OpenSees, but actually a visual representation of OpenSees. So except from the CAD part, okay, you have all the portions here from definition down to analysis steps that are very similar to OpenSees. So for example, a linear time series, you can see
it's really good.
again. Okay, so I think, Pavan, do you think I'm running out of time? Because otherwise we can go to the questions, because I only wanted to show how to include beam column joints here, but I'm having this kind of problems.
Yeah, so I mean, we can have questions, and once you have the internet like fixed, maybe you can go back. How about that? It's up to you. I mean,
no, for me it's fine. So for some reason I'm having problem with the remote desktop here.
Okay.
To connect again, but that was the only last example. I will send it to you anyway, and you will see how. Okay.
Yeah.
Oh, here I am. So basically, it's just.
I mean, for us, it's early morning, so we are not in. For you, it's the problem is from like for the people who are having.
Yeah, I imagine.
And like.
Yeah. Okay, so basically, the last model that you will see is this one. I'm not going to talk too much about it, so you can have a look at it. As you can see, the geometry is a simple connection of frames and the master node for the floors. There is no duplication of the nodes, but then we created a simple Python automatism. Okay, it's a simple Python automatism that you can assign directly to the node, and this automatism in automatic can write a TCL file with the separated nodes, create the joint offset, and so on. So just what I wanted to tell you is that all the parts going from definition down to the analysis steps, and here you can recognize all the pieces of OpenSees that you have here. So we didn't try to change any name. You have the description of OpenSees. So if you're familiar with OpenSees, it will be very easy to use this one. And all these components are actually open source and written in Python. Okay, so everyone can customize it. If you have new elements, you can introduce them. So it can be very easy. So this is the main reason why we decided to create this tool. And in the new version that is going to be released in a couple of weeks, we will be able also to access the database via Python. So actually from the post processor, you can actually change the results or combine the results and do your own evaluation. Okay, so I think I got run out of time. So if you have any question, please.
Yeah, thank you, Massimo. Like it was really good. Like for someone who is starting, all these differences will be really helpful, I think. And yeah, they can use this as a reference, maybe. Cool. And yeah, any questions from anyone?
Yeah, hi Massimo.
Hi.
Hello, can you hear me? I'm Georgia.
Yeah, hi, Georgia.
Hi, thank you for this interesting presentation. It's the first time for me here with you, so It was very interesting to follow you. I have, first of all, I want to thank you for the trick about the GJ value and the section aggregator. And so basically, if you want to put 0 to GJ value, you have to use the section aggregator. And instead, if you want to assign a GJ value different from 0, you don't have to use the section aggregator, is right?
Is right. You have to use the section aggregator only if you want to model the nonlinear torsion, basically. So
Okay.
if you torsion, if for you it is enough to put a linear elastic value for the torsion because you're not interested in the nonlinear torsion response, you can just use the J that is in the fiber cross section because now you are forced to use it. So in any case, you need to put a value there. Otherwise, you will have an error from this.
Yeah.
And of course, it cannot be 0 because otherwise it will be singular in torsion.
Okay.
Instead, you have to pay attention if you want to apply torsion in the section aggregator because depending on the finite element implementation, they will behave differently, okay? So the common rule is 0 if you want to use torsion in the section aggregator, or use a real value if you don't want to, okay?
Perfect. Thank you very much.
Welcome.
Any other questions?
Yes, Pawan, I have one question.
Go for it.
Okay, thank you. First of all, Massimo, you for the very well explanation and presentation. I have one question regarding the lump plasticity and distributed plasticity approach which you showed. It's actually you showed, I mean, the example and the response, the result you showed is a one column result. But what we have, if we have a large structure, and if there is some possibility of short column failure mechanism. So I don't think the results would be the same for both approaches. I mean, lump plasticity and distributed plasticity.
Actually, short columns, then of course you have to include shear deformation or some kind of shear failure. In that example, I only made a comparison on the PMM interaction, of course. So I did not no comparison for shear. In that case, you have to include transverse shear somehow, okay? But in general, the other problem that you have, the first one is shear. The other is the fact that in lump plasticity, you don't have a dependence on the axial force. Now, in that case, it was perfectly matching because I calibrated the moment curvature response from my moment curvature at that value of the axial force. But of course, if you are doing a more complex structure where you have a redistribution of loads and the vertical loads may change during the analysis, of course, they will not match. Okay, so probably if you want to gain time by avoiding putting nonlinear material in the middle, I think the best choice is to use the beam with hinges element, because of course you have to pay for the extra cost of having fiber cross section at the ends, but you have dependence on the axial force. But in the middle, you can use an elastic element, so you can save a lot of time, and you don't have to worry about the strain regularization. So typically, I tend to use the element in the middle here when I want to gain, when I don't want to take care about strain regularization, and when I want to spare some time, gain some time avoiding nonlinearity here in the middle. Okay.
Thank you.
We have a question from here.
Hello, Professor. I'm a PhD student in University of Auckland, and I've noticed that in your example you used the modifier K material, as there are several editions about that material. I wonder if this STKO software includes those different edition material.
Sorry, I didn't understand the question. Do you have problems with STKO?
No,
No, go there.
Okay. I'm curious about, as I noticed that you have used the modified MK for your example, and
yeah.
I've found that the modified MK have several editions, several update editions in the GitHub website, and I wonder if this STKO software, including those different editions?
Yeah, actually, yeah. I think I saw that in the blog of Professor Scott. Is it that you are referring to? Because I've seen in some blogs that there were problems with those material models, and I think we have included them because they have been included in some of the latest version. Let me see.
Okay.
They should be under materials, uniaxial. In any case, if you want to find something, you can find the same tree here that you have in OpenSees. So it should be under other uniaxial material, and they should be the number 02, right? The fixed one.
Yeah. And okay.
And pinching 02.
Oh yeah. And there now.
I think it's IMK by Lin, IMK peak oriented, IMK pinching, right?
These ones.
Yeah, those are the new ones, I think.
Yeah.
And in any case, just since we are here, whenever you have some material that are missed, or sometimes, for example, we try always to be updated with OpenSees, but sometimes since OpenSees is open source, you can have your own OpenSees, do your own material model that probably are not in the public repository. Of course, SDKO cannot be aware of that. In those cases, you can simply go into the SDKO installation folder, just to show you how it works. And then inside SDKO, all the things that you see here, from definition down to the analysis steps, are inside the external solvers, and they are all Python. So let's say you want to include a new material model, so okay, that is not available in SDKO. You go under physical properties. If it is a material, you go under material. If it is uniaxial, you go here, and then you create your own. Okay, it is a simple Python script, just a couple of functions. So I'm not saying it is easy, but you can define how should be the user interface of SDKO and how those data will be written in Tcl. Okay, so it's true, SDKO is not open source in the CAD part and individual part, but in the connection it has with OpenSees, it is completely open source. Okay, so you can do your modification, or if you find bugs, for example, you can fix it. If you can add your own material model and so on.
Okay, thank you very much.
Welcome.
Any other questions from anyone?
I have a question. Massimo, nice presentation. On the member loads analysis you did, I don't know if we have time, but if you just made it pinned instead of fixed, you would get some internal moment in the displacement-based element, right?
Yeah, I think I will have it. The point is that
I think it'll be constant. I mean, it won't be accurate, right? But it'll be something,
exactly,
but not constant or not zero, right?
Let me do a test. Yes, in fact, I didn't test that one. Yes, I was expecting not to have that when everything was fixed, because of course there was no strain. But let me do that test. So I go beam element loads, and so the mesh should be, okay, only one mesh. And fixing the bottom, I just fixed the rotation about Z. Okay, but also the rotation about X, only in 2D. So rotation about Y is free, and rotation about Y will be free also on top. Rotation about Y, okay. Just one element. Element flow, here it is. So one element, beam diagram. Of course it will be, because now we see, actual force is actually small here, but let me see, My, yes, I have it. My, step 1. This is local forces, sorry, I need to visualize in section forces. Local force will always be there. So section forces are at the Gauss level, and Y. Yes, they are, and it is constant. Is it actually, the entire area should be the same as this one, probably? It should be probably the same amount, but it is constant, yes. Yeah, so basically the only, one should take care of the fact that, well, as usual, it should be discretized also for this kind of topic. Yeah, thank you, Professor Scott.
Yeah. Oh, sure. I just wanted to make sure it was something should get in there, but it's just the boundary conditions, right? Because it's the equivalent nodal loads are applied on fixed boundaries, so nothing happens, right?
Yeah, exactly. While here, since you do iterations, of course, and you put the external load during the iteration, the element will compute the trial strains according to those forces. That's why it goes completely inside the sections.
Yep.
Okay, so thank you. Is there any other question?
Yep. Any other questions? Looks like no additional questions. Cool.
Okay.
Cool. Thank you. Thank you everyone for attending. Thank you, Massimo, for the presentation. I mean, if you have any questions, please, feel free to ask him, I guess, like send him an email, or he's super active on OpenSees Facebook group as well. So
yeah, I will message you just to ask you how we can share those files.
Okay. Sure. Okay, cool.
You can host it, but if you have some links and you want to host it on your website somewhere, we can send it to you. So
I don't have a website. I'm like still a student. I don't have a website.
Okay, so if it is for you, we can host it on our website, and then we can send you a link. So if
cool.
one of the others want to download those files,
I think I got an idea. I'll just discuss with you. Maybe you can upload it on your website. I can get the link and I will post it on the YouTube link below, like in the description, where they can download along when they see the video. So
of course, I will do it tomorrow morning because now it's late.
No, that's fine. That's fine. Whenever.
Okay.
I understand. Cool. Thank you for your time again, and it was really good. So, thank you, everyone. See you in 2 weeks on December 15th. We have Dr. Michael Scott presenting, and he will be talking about how to implement a uniaxial material if you want to add your own materials or do your own materials. So that would be pretty interesting, I guess. So we are looking forward to that, Dr. Scott.
Okay. Thank you, everyone.
Thank you. Good night, guys.